introducing our second keynote speaker, Wen-mei Hwu from University of Illinois Urbana-Champaign. Wen-mei is the Sanders AMD endowed chair in ECE at UIUC, and he also has a startup company. I'm not sure if it's a startup anymore, but he's the CTO of Multicoreware. And he definitely doesn't need an introduction here also, but I will do it justice and do it with slides. Wen-mei has had an amazing career so far, and he has a longer career than Yale probably going forward, although Yale probably argues about that. But he's received the first inaugural Morris Wilks Award given to a young computer architect at that time, Great Software Award, Brow Award, and the ISCA Influential Paper Award for the Impact paper, and many other honors that I'm not going to list over here. He's had many wide-range contributions, including the HPS papers that I showed you earlier, checkpoint repair for auto-order machines, superblocks, impact compiler, hyperblocks with the students, and many compiler optimizations building upon that. And I'd like to point out that one of the earliest adaptive cache management papers, also with Teresa Johnson, was from Wen-mei too. And later on, he has switched to GPUs and did a lot of optimization work on GPUs, both compiler and hardware. And he has a GPU book with David Kirk, which I will show. I'd like to point out one unique contribution that has been important in my development, my personal development. I don't know if Wen-mei knows this, but during graduate school, Yale had received videotapes of Wen-mei's compiler class. I believe it's ECE 512, although it might be 5112. But I learned a lot of compiler optimizations and hardware-software interaction techniques like modular scheduling, how to handle fetch breaks, both in compilation and also in hardware, from those video lectures. And I think at some level this has inspired me to put my own lectures online so that other people could benefit from those lectures. So thank you for that inspiration. But I'll go through some quick overview of the papers that Wen-mei has done. This is one I like. This may be something that Yale and Wen-mei have a common shared memory with. So maybe you can tell them about that. The impact paper, certainly this is the one that received the Influential Paper Award. The Superblock paper, which was published in Journal of Supercomputing in 1992. And this is the cache paper, which many people actually, I don't think they realize that this was one of the earlier cache optimization papers, calc optimization papers that were done. And the book by David Kirk and Wen-mei Hwu, which many people over here, I'm sure, know. So I'll leave it to Wen-mei to deliver his keynote. Thanks.
Thanks for the very generous introduction. Can you hear me in the back? Mel, can you hear me? Can you hear me in the back?
I think the mic is not.
Mic is not on.
There's a button you can press.
Maybe there's a switch.
Can you hear me in the back?
Yes.
Yeah.
Good, good. Okay. So thanks for the very generous introduction. And when owner invited me, I started to realize that there's a reason why owner invited me. Yale was going to give the first keynote, and very few people are willing to go after Yale. It's very hard to match Yale. So I'm not going to even try. So I'm going to be just here to talk about a few things that I probably learned from Yale over the years. And Yale is in the back, and so hopefully I will build on his talk yesterday and then provide a little bit of perspective here. So let me start. There are four things that I'm going to try to cover today. One is, I'd like to talk about some revolutionary paradigm shift that I have been seeing in the field. In my spare time, I have been one of the principal investigators of the supercomputer project called Blue Waters in Illinois. And my primary job is to work with several science teams to make sure that they are able to use what we call the leadership computing and do breakthrough science. So I'm seeing quite a few interesting application level changes in the past several years, and I'd like to share some of the thoughts with you. And then I'd like to talk about architecture and technology pivoting. So I have a little bit of perspective about how we got here, and where we probably be going in the next few years. And then I would use an example of positive application technology spiral recently, and many of you have seen the deep learning development, and I'd like to also provide a little bit of a perspective. And then I'll talk about engineering high efficiency software for heterogeneous computing. What Yale did yesterday was exactly what I was hoping him to do. He gave you a very, very fundamental treatment of latency versus bandwidth, and some of the things you will actually see in the talk today. And what we actually come up with, again, some of these things all the time. And hopefully, it will be a kind of an interesting combination from your perspective. What we have been seeing in the past, I would say 20 years or so, is an interesting paradigm shift. In the 20th century, we had tremendous technological improvements. For example, if we look at the semiconductor application, we went from, in my graduate school days, people were saying that 1 micron technology was not possible. And we all have seen articles that the 1 micron is going to be the hard limit. And we passed that with flying colors, right? And towards the end of the century, we started to have, get into the deeper submicron technologies. And so, basically what we're able to do is to combine the physical instrumentation with computing. And we're seeing better and better, ways for people to produce these masks, and then, controlling the light sources and so on. So that's just one example. And we're going to see some, comparison and contrast. So basically, we're able to, see farther. For example, if we look at the telescope world, the world has made tremendous progress in terms of the telescoping technology, that we are able to use the radio waves and so on in a much more effective way, plus signal processing technology in the computing. So that was what we did in the 20th century. In the 21st century, what we're beginning to see is, I would say, explosive usage of computing for various things. For example, many of you have seen some recent announcement in astronomy, so the dark energy and so on. And all these things were only possible with computing. And if you look at the Nobel Prize announcements and so on, the computing model and computational resources were really the key for these people to be able to advance that theory, and then being able to validate the theory with observation through the computation. So we're able to see even farther, and in many ways the computation model also allows us to go back and forth in time, which is impossible to do with pure observational instrumentation. So the computation model enables us to be able to go back and forth in time and test out some of the hypotheses that was just not possible to do with physical instrumentation experiments. And we can create some safe artificial processes, and I'm going to come back a little bit more. So if we look at the 20th century, there are some interesting examples that we can compare and contrast with the 21st century. For example, in the semiconductor business, in the 20th century, we get smaller and smaller patterns on our masks. But in the 21st century, if you look at those masks, you have no idea what that mask is supposed to be doing, because those masks are generated by optical proximity correction algorithms. They intrinsically assume that the light sources are going to be interfering with each other, so they actually compute all these potential interference patterns, so that the light sources will form the right kind of pattern after interference onto the semiconductor surface. And that particular process is an extremely expensive computation method. It's not even possible to produce those masks without the proper first principle based light modeling. And this is actually a theme that I'm seeing all over the fields. Many people are beginning to be able to use more first principle based models to be able to do some of the things that people previously considered to be too expensive and too costly to do. For example, if you look at medical imaging, we all know that medical image came a long way in MRI and so on. But one of the things that all these people are now telling us is that they now want to be able to go back to the first principles and reduce a lot of these approximations they had to make in the 20th century in order to make these things practical in the 20th century. For example, if we look at even the simplest ultrasound imaging modality, the ultrasound world is now they will tell you the traditional ultrasound reconstruction was based on a simple model where you only assume that the sound wave is going to be bounced once. But that's clearly not a reality. So the model that they're now deploying is based on essentially the same principle as the ray tracing technology, and they're able to use multiple bounces and create much more accurate image. And that also coupled with the ability to solve extremely large-scale inverse problems, give these people the methodology to be able to see much better into the internals of our bodies and so on. So we're seeing, for another good example is electronic microscope, and that in the 20th century, these electronic microscopes was able to be combined with crystallography to be able to begin to see dead viruses. Essentially, you have to kill these viruses in order to be able to see them in a microscope, but then at least we're able to begin to see these creatures. But in the 21st century, what people are doing now is they use crystallography to be able to set the initial condition of a molecular dynamics-based simulation model of the virus so that they can actually see the virus in action. So there are all these other things like anatomic imaging with computational imaging and processing, but if you look at the forefront of medical imaging, most people are now moving on to metabolic imaging. Essentially, the imaging is no longer looking at the anatomic change of our body tissues. It's actually looking at the chemical process of our tissues so that they can begin to detect potential change to our anatomy, because of the disease or because treatment, so that they can predict the development of disease rather than spotting the disease after the development. So teleconference versus teleimmersion and GPS technology that we used to have to be able to tell where we were, and that was very much an achievement of the 20th century. But for the 21st century, as Yale properly pointed out, we're going to have these silly cars driving themselves around, probably in California highways, not quite in Manhattan yet. So but that's where we're going in terms of these computation versus instrumentation-based approach. I hope I made my point clear with these slides. So let me go a little bit deeper into what Yale was saying yesterday. So if we dive just a little bit more into the computational microscope technology, and this happened to be a particular science breakthrough that I'm personally very familiar with. Klaus Shelton's group in Illinois is driving this whole movement with several other collaborators. So I'm actually seeing their kind of a regular advancement on a regular basis. So when we look into these things, fundamentally, these microscopes are based on molecular dynamic simulation. They simulate the actions of atoms and various particles in solvents so that they can produce the kind of biological observations. So if we look at the two fundamental driving forces for enabling this particular type of application, the large clusters allow us to simulate biological systems with realistic space dimensions. And this is, in general, what people call the scale out. So if we look at the typical process, we need to have about 0.5 angstrom. Each angstrom is 0.1 nanometers. lattice spacing in order to have the accuracy. So these things are not that different from weather simulation systems. They all are based on some sort of gridding system, and then you take all the simulation of particles and then accumulate some sort of potential, some sort of force, some sort of acceleration, into these gridding systems. So the interesting biological systems have dimensions of millimeters or larger. So these are your observational samples. So these things are in the order of millimeters or above. So in order to be able to simulate such a system, if you divide up a millimeter by something like 0.5 angstrom, you get a fairly large number of grid points in each dimension. And that's the physical size of the system that you would need to have in terms of the DRAM requirement, in terms of what the number of calculations that you have to do on a time-step basis to be able to simulate such a model. So that's why thousands of nodes are required to hold and update all these nodes. So this is driving the sort of the petascale, the exascale machine sizes. For example, the Blue Water supercomputer today has 25,000 nodes, and each node has 2 sockets. So that's where what we are in terms of these kind of technology. But there's one factor that is oftentimes overlooked. That is what Yale was talking about yesterday. You can roughly translate the large clusters here as sort of the throughput, or the bandwidth kind of argument that Yale was making. But it turns out that there is another very important dimension, which is the fast nodes. The fast nodes allow simulation at realistic time scales. In order for these kind of systems to work, you have to be able to simulate at fairly fine time scale so that all the differential equations will work, solution will work correctly as you solve these equations over time. And the simulation time steps are in the order of femtoseconds. So that's 10 to the 15th, negative 15 seconds. In fact, femto is the inverse of peta, right? So for those of you who love these numbers, that's how you can kind of, it took me a while to get used to all these numbers when I got into the supercomputing world, and people are just talking about all these numbers, and I had to put together a little table to see, to have a real sense of exactly what these numbers are. And for those of you who don't have a real sense of what a petascale computer is or what an exascale computer is, what I suggest is that you would write your name 1,000 times, actually 1,024 times. And I knew exactly how long it took, because when I was an elementary school student, I talk a little bit too much in class. So my teacher always keep me after class and then write my name 1,000 times. So that trained me into a good engineer and a very bad handwriter. So but once you wrote that 1,024 times, you take that time, multiply by 1,000, that gives you a meg, right? And then you multiply that by 1,000, that gives you a gig, and then multiply that yet by another 1,000, that gives you a tera, and then you multiply by another 1,000, that gives you a peta, and then multiply by another 1,000, that gives you exa, right? So if you find all that time, you will realize that you may not be able to finish writing your name that many times in your lifetime. Okay, so that's kind of how these scales work. So for the fast nodes, in order to simulate an interesting biological process, the biological process takes time in terms of milliseconds. And that's actually a fairly fast biological process. Many of these biological processes happen over seconds or minutes, and sometimes even more. So the milliseconds are the bare minimum that we need to be able to simulate in order to produce meaningful results. That's why the current molecular dynamic simulations are not fast enough. If you look at the standard way of using the various molecular dynamic tools, such as NAMD, such as AMBER, the fastest the fastest rate at which they can simulate a biological system is actually about 1 day for each 10 to 100 microseconds. So you will need to spend a simulation time of a whole day in order to simulate that system for about 10 to 100 microseconds. And this is the reason why, you know what, it doesn't matter how big your system is, it's not going to improve that time. It's how fast your individual nodes are, and also how fast the latency of the network really matters here. And this is the reason why, you know what, we have people like E. Shaw who will build these, you know, custom molecular dynamics systems. He's actually spending hundreds of millions of dollars of his own money trying to, you know, to improve this latency. And improving this kind of latency is extremely expensive. And in the past 10 years, the latency of these simulations have been driven by GPUs. And the CPUs have not been able to improve the simulation time of these kind of devices, you know, significantly for the past 5 years. On the other hand, you know, well, we do expect that some of these you know, technologies will come in. For example, the high bandwidth memory and so on that will you know, improve this kind of simulation. So what does this do for the field? So this is a Nature article that came out not too long ago. And so this is the first real study that is actually validated by experimental groups of how the HIV virus was able to, you know, to actually you know, disassemble, release the genetic material into the human cell. So this is the first time that the scientists were able to have a credible you know, simulation result showing how the HIV virus actually infects humans and how that process could be used as a target for drug treatment, right? So these are, this by no means a solved problem, but this is the kind of progress that people are able to make with the kind of machines that we're talking about. So that's the application world. We're seeing, you know, people with bigger and bigger appetites in, you know, having all these machines, and this is the fundamental reason why, you know, the governments are spending billions of, hundreds of millions of dollars to build these exascale machines in the future. And you know, there's also the reason why people are not just trying to build bigger machines. People are spending a lot of time and energy trying to find faster nodes for these machines and better interconnects for these machines, because in the end, it's not just the bandwidth. The latency really matters, you know, when it comes to a lot of these breakthroughs. So where are we in terms of the fast nodes? There are a few things that you know,